And the stories are based on work with Emil Martinek and Stefano Masai, mentioned here, including work in progress. And the second part of the story will be work in progress with my postdoc, Sasha Chukov. All of these people are here at the workshop this week. Okay, so I have the liberty of speaking on day 4, so I will keep the broad introduction relatively brief. Suffice to say, we heard lots of interesting discussion on Monday, motivating that now the time is ripe to further the exploration of the microstructure of black holes. And we've also heard that in string theory, there's been a lot of progress over more than 20 years of describing heavy, pure bound states of strings and branes using both smooth horizonless supergravity solutions as well as their more stringy counterparts. And by this, I mean configurations which contain explicit sources and or conical defects and or extrapolations of smooth horizonless supergravity solutions into regions into parts of parameter space where there may be regions of high curvature where we don't strictly trust the supergravity approximation. And so here's a cartoon of that. Far away from this bound state, we may have a nice, good semi-classical supergravity description. If we go close in, we may need more of the ingredients of string theory to resolve the fine microstructure. And smooth horizonless microstate geometries and these more stringy counterparts, as you know, are interpreted in the context of the broader fuzzball proposal, which I would state concisely as claiming that quantum effects are important at the scale of the would-be horizon due to the finite size of the underlying bound states in such a way that Hawking radiation is unitary. And as we've heard, this would resolve the black hole information paradox. So this talk is going to be about the interaction of these heavy, pure bound states and relatively light probes, where relatively light will often mean supergravity massless quanta, but also may mean massive string states. And just to state, as we heard from Josef, that there's a long history of these constructions of supergravity solutions, many of which with the same charges as supersymmetric black holes and with all topological bubbles deep inside a long black hole-like throat. And there's a very incomplete list of people who've worked on this problem for more than 20 years. So as I said, there will be 2 stories in this talk. The first one will be in some way a development of what we heard in the first talk this morning. It will describe work in progress on probing a particular family, using a particular family of worldsheet COSAT models, probing the physics of a set of supergravity backgrounds known as spectral flowed circular supertubes with NS5 F1P charges. The physics I'm going to be interested in is that these backgrounds have ergo regions. And there's interesting physics associated with those ergo regions, which the physics depends on whether the background is supersymmetric or non-supersymmetric. And the interesting physics relates to scrambling, or in the non-supersymmetric case, instabilities. In the second part, I'll briefly review the Lin-Lun-Maldacena geometries in ADS5 times S5, and describe some work in progress on computing heavy light correlators on those backgrounds. Okay, so the first part is about supertubes, ergo regions, scrambling, and strings. So just to be concrete, I'll work in the NS5 F1P system. This is the same system that Emil was reviewing in the first talk. I'll work in type 2B string theory on a compactified on T4, where we'll have the radius of S1 denoted by Ry. I'll have N5 NS5 branes wrapped on all 5 compact directions, N1 fundamental strings wrapped on one of these, which I'll denote S1, and NP units of momentum along the same S1. And when we have a geometrical description of such bound states, we have supergravity charges proportional to the integer numbers of branes and other quanta. I'll be working again in the NS5 decoupling limit that Emil already mentioned, which is obtained by scaling the asymptotic string coupling to 0, holding fixed a combination of length scales in string units divided by g-string. So r is a radial coordinate here, r divided by g-string, l-string. And we'll also work at large ry in the supergravity regime, and that gives us a multiple hierarchy of supergravity charge radii scales. That Q5 will be the biggest scale, followed by Q1, Qp, and eventually the string scale. So pictorially, what do we have? Well, the full solutions before taking any decoupling limits have this flat asymptotics, which is R4, 1 times S1 times T4. And we have two intermediate regions, a 5-brane region and an ADS3 times S3 throat, before the details of the microstructure deep inside. So after taking the NS5 decoupling limit, we're zooming in to the 5-brane throat. So we send off to infinity the flat asymptotics. We don't see that anymore. And it's in this limit where we have a worldsheet description, but we still retain two different regions characterized by being linear dilaton dominated or ADS3 times S3. And one can take a further ADS3 decoupling limit by sending Ry to infinity, and there we zoom in only to the ADS3 times S3 IOR region, and that's where we have ADS3 CFT2 holographic duality. So Emil already mentioned the two-charge profile, so I will not give a very detailed introduction to that, but I will piggyback on that discussion. And so to motivate the configurations I'm interested in, let me begin by saying that I want to consider variants of the biggest, fattest supertube that this fundamental string can arrange itself into. So the most maximally rotating solution is described by a profile which is a helix. It's a profile in the covering space, and so when we go to the physical space, this is this kind of rotating barbershop type configuration that Emil had. So the configuration has a lot of angular momentum. This solution for k equals 1 is a completely smooth horizonless supergravity solution obtained by spectral flow of the vacuum ADS3 times S3. I'm also interested in backgrounds which are obtained by orbifolds of that configuration. So this parameter small k will be an orbifold parameter. And so I'm just picturing here the fact that when you have this parameter k bigger than 1, the whole configuration wants to become more compact. And when you choose the profile to wind around the same kind of circle many times, this results in a conical defect, an orbifold singularity in the core deep inside the ADS3. And so there's a family of solutions here, which so far are just two-charge solutions. I'm picturing them in the NS5P frame, where the NS5, I'm just plotting the effective string after we reduce on the T4 directions. So the main focus is not going to be on those two-charge solutions, but rather on three-charge solutions which are obtained by spectral flow from those seed solutions. And so I'm going to keep k generic, k to be bigger than 1. And when I do so, I have both supersymmetric and non-supersymmetric solutions obtained by spectral flow. And in general, because k is bigger than 1, I have a family of solutions which involve fractional spectral flow. What do I mean by that? Well, I have two parameters in the CFT, for instance, which correspond to left-moving and right-moving spectral flow. And in the CFT, typically we do spectral flow by integer units. But when k is bigger than 1, there is an enhanced allowed values of spectral flow. Because I can take the whole CFT, for instance, to a covering space in k and do spectral flow in the covering space. So that gives me a parameter s, such that the spectral flow is s divided by k, and the same on the right-moving sector, s bar over k. When I make this operation, I end up with states which have rotation, more rotation than I started with. They now have three charges. I'm adding energy to the system. And the holographic description involves a filled Fermi sea. So there are states which are highly rotating for their energy, but are very simple to describe holographically and relatively tractable also in the bulk. This spectral flow parameter S over K corresponds to a simple large coordinate transformation in the supergravity. Yes?
So in the J-Mart solutions, you have Fermi seas in both left and right. You don't have anything other than a Fermi sea.
Correct.
Okay. So that's why you don't have entropy.
Yes, yes. These states are, they are not in general unique for their charges.
Yeah.
When k equals 1, they are unique.
Yeah.
For general k, there are degeneracies, so there are nearby states. But these states are very particular and specified by this Fermi sea property.
And the two Fermi seas are independent.
Yes, absolutely. So I have these independent parameters in the left and right of the CFT, so I can tune them as I like, subject to a condition, which is that there's a quantization of overall net momentum per strand of the CFT. Thank you. Okay, so I mentioned that this fractional spectral flow corresponds in supergravity to a large coordinate transformation. So it's simple to write down the ADS3 decoupling limit of these solutions, where here I'm focusing just on the supersymmetric subset of solutions. And so in the supersymmetric case, when we take the ADS3 decoupling limit, these solutions are just rotating analogs of global ADS3 times S3. The spectral flow is this large coordinate transformation that you can eyeball here. It's a mixing between the angles on the S3 and the time and S1 circle of ADS3, and such that if you were to undo this large coordinate transformation, you could map yourself back to global ADS3 times S3. Okay, so I said I wanted to talk about ergo regions. So just so we're all on the same page, let me define that. An ergo region is defined to be a region of space-time where an asymptotically time-like killing vector field becomes space-like. Now, that's a simple definition, but if I have a space-time with an asymptotic Kaluza-Klein direction, so a finite-sized compact direction, that definition is not unique. So if I have finite-sized compact directions at infinity, there are families of asymptotically time-like killing vectors, parameterized by one or more continuous parameters, one for each direction, each Kaluza-Klein direction. And so I have to first tell you which asymptotically time-like killing vector field I'm interested in. And with respect to that asymptotically time-like killing vector field, we can ask whether or not there is an ergo region in the space-time. Moreover, since I'm interested in taking decoupling limits change the asymptotics of the space-time. And so they can change the property of, firstly, whether a killing vector field is asymptotically time-like or even normalizable. And it can also, in principle, change the statement of whether there is an ergo region with respect to that given vector field. So an interesting question to ask is, in this case, when we have Kaluza-Klein directions at infinity, whether for all possible choices of an asymptotically time-like killing vector field, there is always an ergo region in the space-time. And that's a much stronger question than asking for any given vector field if there's an ergo region or not. When the answer to that question is yes, the space-time is typically unstable to particle creation. And you can see that in linear perturbation theory. There are unstable modes. The asymptotically flat J-Mart solutions, so that's the solutions with general left and right spectral flows that I've been talking about, exhibit precisely this phenomenon. So this is an instability in linear perturbation theory, and the ergo region instability of these J-Mart solutions was interpreted holographically as a classically enhanced analog of Hawking radiation. So of course, Hawking radiation is a quantum effect, and h bar can be thought of as like 1 over n. So for thermal states, there's a vertex operator in the holographic CFT, which describes the thermal radiation of Hawking radiation. Because these states are very coherent, there's an enhancement of that 1/n effect. It gets effectively multiplied by a power of n to the 1, such that this radiation is classically visible for these particular solutions rather than quantum. There's a question. Samir?
Do you need a sufficient angular momentum in order for the error region to exist?
The question is, do you need a sufficient angular momentum for the ergo region? So I think the answer is probably yes. I mean, within this space of solutions, the ergo region is definitely there because of the rotation. And but I guess you're asking more generally about a more general class of solutions.
I think that you can have it with arbitrarily low angular momentum.
Okay, comment at the...
So maybe just as a comment, so I think you could even have zero angular momentum but charge, right? Because if I think about the classical black hole, Rice and Ostrom can have these ergo regions too.
Yeah.
So maybe that helps to clarify this.
One way I can give an example of what Roberto is saying is that this parameter k, if I increase k, the angular momentum decreases linearly with k. So if I crank up k as much as I want, I can decrease the angular momentum as much as I want. I'll still have an ergo region. So it's not the absolute value of the angular momentum per se.
Even without cranking up k, right? Because what you're doing is you're having some Fermi level, and this Fermi C can be as small as you want.
Yeah, S can be small, and yeah. So angular momentum is also controlled by S. So there are two ways I can reduce the angular momentum. Indeed. Yeah. Thanks. But that will give me. I mean, it's still angular momentum is like S over k in units of capital N. So taking S to be 2 it's still 2 times capital N. It's really by cranking k. If I make k of order n, that's where I make the angular momentum to be microscopic rather than large. Okay, so good. Now that was a comment about the instability of non-supersymmetric solutions. By contrast, I'm interested in the supersymmetric solutions and their ergo regions. So the supersymmetric solutions, by contrast, are not linearly unstable, and the simplest way to see that is to note that they have a globally null killing vector field, which is guaranteed by supersymmetry in 6 dimensions. So that means that there is a boosted frame, an infinitely boosted frame, with respect to which there is no ergo region. And correspondingly, there's no sign of any linear instability in the background. So this was some discussion also in day 1 and maybe day 2 about evanescent ergo surfaces. Let me connect to that language. So an ergo surface is defined to be a hypersurface on which an asymptotically time-like killing vector field becomes null rather than space-like. And typically an ergo surface is the boundary of an ergo region. However, an important feature of many smooth horizonless microstate geometries is that they have ergo surfaces which are not the boundary of ergo regions. They're just locuses deep inside the core of the solutions. This is especially seen in supersymmetric solutions in 5 dimensions. And these are known as evanescent ergo surfaces in the sense that there's no finite size ergo region there, but if upon some deformation, you may see some finite size ergo region. These evanescent ergo surfaces are nevertheless very interesting because they're loci of infinite redshift deep inside the core of the solution. So if excitations can be localized there, they will have 0 or nearly 0 energy as seen from infinity. And so you can imagine sort of a mini version of a bag of gold there, where you can pile up local excitations at almost no cost in energy as measured asymptotically. And so my story is mostly in 6 dimensions rather than 5. But if I would dimensionally reduce from 6 dimensions to 5 dimensions, the solutions I'm telling you about, the supersymmetric spectral fluid circular supertubes have evanescent ergo surfaces in the core, moreover on which there are stably trapped null geodesics. So this was again mentioned on day one, this phenomenon of stable trapping. These solutions are a prototype of that phenomenon where the excitations which are localized near this evanescent ergo surface are energetically trapped. And there are null geodesics which are stably trapped. So if they can accumulate near the surface, they find it very hard to escape. There's some energy barrier for them to do so, and in the linear analysis they have tiny imaginary quasi-normal frequencies, but one can think of them as needing to tunnel out of an energy barrier to actually escape from the core of the solution. And so that's interesting when we think about scrambling, because when we think about perturbing such a microstate geometry to being slightly non-BPS, we can ask, we give it a little bit of non-BPS energy, we expect it will want to relax back to some BPS or near BPS configuration. So one thought experiment that was proposed several years ago now is to consider a massive probe particle coupled to supergravity fields, and consider dropping it into the space-time and allowing it to settle down and gradually radiate soft modes and lower its energy. Then where's the lowest energy place it can end up? Well, it's next to this, localized near this evanescent ergo surface in the core of the geometry. And so then the local energy, as this approaches a null geodesic, the local energy will be very large, and that will indicate a potential nonlinear classical instability associated with this back reaction. So that's all a story in classical field theory, and that's the language of the classical analysis. But I think a better terminology for this is scrambling. This is describing how these supersymmetric solutions scramble perturbations. So there's a story of a few papers here where, firstly, for two-charge microstates, this process was modeled with previously known two-charge Lund-Mathur solutions involving shock waves, where near this evanescent ergo surface, you model the back reaction of such a probe by a smeared shock wave. And this has the effect of reducing overall the angular momentum of the configuration. This was interpreted as an evolution to more typical microstates. And if one thinks holographically, one gets a little bit, I think, better perspective on this scrambling phenomenon, where this the ability of the background to scramble and lower its angular momentum is constrained by the energy you supply. So if you give it just a tiny kick, it cannot run away and radiate all its angular momentum all the way down to zero. You need to either kick it repeatedly or give it a lot of energy, and then it has the chance to scramble into a larger space of nearby states. So motivated by this, we constructed deformations of these three-charge circular spectral fluid circular supertube containing shock waves in their cores. And there's interesting physics that comes out of it, because although I told you that the six-dimensional three-charge spectral fluid supertubes have a globally null killing vector field, if one takes the canonical time-like killing vector field at infinity and asks, is there an ergo region in 6 dimensions? The answer is yes. And this has been noticed long ago, actually in the paper of JMART, whose primary focus was the non-BPS versions of this, but they commented on the supersymmetric solutions at that time as well. And so that means that there are perturbative excitations in the ergo region such that they cost you negative energy as seen from infinity. They reduce the overall energy of the bound state, but in a BPS way, in a supersymmetric way. And that's possible because the particle or the shock wave is resisting the rotation in the background. It's attempting to counter-rotate relative to the background, and so it's reducing the chiral energy of the bound state. And in the holographic CFT, you can understand that this process is, this fact that there are negative energy excitations is due to fractionation. So, okay, I don't know whether the bottom of this plot is beyond your horizon, but just to flash briefly some of the states which are, and their quantum numbers which are in this space of solutions. So here I'm plotting both the spectral flowed supertubes without shock waves and also a subset of the shockwave solutions. So I'm not showing you the explicit solutions, but here I'm plotting an angular momentum against the y momentum np. Okay, all units are in, everything is in units of capital N. The parabola here is the BMPV parabola, so the region of parameter space inside here is where there is the single-centered large black hole. All of the solutions I'm talking about are outside of that regime, so they don't have the same charges as large supersymmetric black holes. And what happens is that these dots are the solutions without shock waves, so they can be quite far in some cases from the BMP regime, or in some cases they can be somewhat closer, and that's quantified again by this parameter k. So everything is in units of n. So when k is bigger than 1 but not scaling with n, this is still a macroscopic distance between the dots and the parabola. I would have to crank k to be scaling with n to get this to be as close as we would want. And the thing that I want you to notice from this is that there is some somewhat arbitrary but nevertheless correlated color coding between the dots and the crosses. So if I start from this solution here and I add a shock wave, then I have two BPS solutions, and these are related by the shock wave taking away angular momentum and y momentum and energy in a correlated way, such that we have a shock wave inside the erg region. The energy of the state I started with has been reduced, but everything remains supersymmetric. Question?
Can you explain what happens to the shock wave when it propagates in the interior of the geometry? Can it reflect back from the circular supertube? Can it destroy the supertube and destroy the shape? And
okay, this is a more dynamical question. These solutions are not, don't quite have the dynamics you're thinking of. So I have some erg region, and I have a locus where the shock wave is being placed. Now, depending on, so when I start, the shock wave is effectively reducing the size of, I need to say the words coarse graining. Okay, so I didn't plot for you the profile function of the solutions with shock waves for the two charge case, but you can think of them as starting with a nice smooth profile and adding onto it some high frequency modes. Okay, so there's some Fourier decomposition of mostly one particular low harmonic, and then some unspecified bath of high harmonics, which are not going to be resolved. The details are not fully resolved by supergravity. They're modeled by the shockwave, which has the usual Eichelberg-Sechsel singularity. Okay, so what it has the effect of is that after coarse graining, the supertube locus is reduced, okay, which it should because the angular momentum is going down, in a way that violates the condition for smoothness, okay, to allow for the presence of the shockwave. So the shockwave has a fixed position, but then what's interesting, so that's all the solutions on this line down here. Okay, so in each case, because the shockwave is rotating in some sense from right to left, it's reducing the angular momentum. What happens is that after you make the spectral flow construction, whether the shockwave is inside or outside the ergo region is not 100% in your control. It's determined by spectral flow. Okay, so in some cases, the shockwave adds energy. So it doesn't have to be in the ergo region, but it's particularly interesting here when the shockwave happens to be in the ergo region.
So I have an elementary confusion. global ADS3 times S3 does not have a Ergo region, and so any.
I've stopped you there. Yes, it does. It depends. Okay, it depends on your choice of time-like. So you can say you can ask, does it have a globally time-like killing vector field? The answer is yes. So there is a choice of time foliation with respect to which there is no Ergo region. There is another choice of time-like killing vector with respect to which there is an Ergo region. Okay.
But that's not due to some funny identifications.
It's just the fact that you have a finite size S3. So there are families of time-like killing vector fields. So with respect to some rotating frame, there is an Ergo region. And so with these spectral flowed circular supertubes, that rotation is built in. So the canonical time of the CFT, with respect to that canonical time-like killing vector field, there is an Ergo region, and there are negative energy BPS excitations, which can be fully back-reacted. Roberto also had a question.
So I think that there seem to be two different ways of constructing these solutions, and I don't know whether they are the same. So you may start with a super tube, you add a shock wave, then you spectral flow. And you first spectral flow the super tube and add a shock wave. Does this give you?
Yeah, so good. So the answer is that what we did was that we first added the shock wave and then we spectral flowed. So the first of those is the solution generating technique we found.
Yeah.
And that's a relatively straightforward thing in ADS because it's just a large coordinate transformation. The non-trivial part is to extend that to a full asymptotically flat solution.
You've done that as well?
Yes.
Okay.
That's non-trivial.
Yeah.
But because it's supersymmetric, you can use the multi-center formalism to do that's the solution generating technique to generalize this from an ADS3 solution to a full asymptotically flat solution.
Is it more like a multi-center, or is it just some other harmonic function?
It's two centers, but not a smooth solution. It's two centers where one of the centers is a singular center corresponding to the shock wave.
Yeah.
So the non-trivial step is to take the solution you get from a large coordinate transformation, rewrite it, decompose it into the two-center formalism, and once you've done that, you can trivially add the one in the harmonic function that will get you back to a full asymptotically flat solution. Here's another comment or question.
So the shock wave is where? I mean, if I have the super tube center, I have the center of space, and I have another Gibbon-Stocking center.
Super tube center.
Oh, it's on the super tube center, so you're putting it behind there. Because you can also put a shock wave at some other distance away from them.
You can, but this is what we did.
Okay.
Yeah.
So it's a pole in the p harmonic function. Is it in the m harmonic function? In the last one.
If I remember, I don't have that slide, but if I remember, it's in more than one component. But we can check back.
Okay. Thanks.
For sure, it affects the angular momentum because of what I've been describing. Okay. Good. So as Emil was reviewing, there's a family of worldsheet models that describe the spectrally flowed circular supertubes without shock waves. And so there are natural questions one can ask. For instance, how is the physics of the Ergo region encoded in these models? For instance, in the perturbative spectrum. And how does this discussion of scrambling and Ergo region instability when it's present generalize from supergravity probes to massive string probes? And so I will go a little bit quickly on the introduction of these models, since it was mentioned in the previous talk. So these are gauged supersymmetric West-Intermittent models, where we start with a 10+2 dimensional target space, and the null gauging removes 1+1 directions. And this is an asymmetric chiral null gauging with null currents J and J bar. And so when we gauge the model and integrate out the gauge fields, we get exactly the sigma model on the background of interest in the NS5 decoupling limit. And so there are various families of backgrounds that can be generated in this way, including 5 branes just separated out onto the Coulomb branch in a circular ZN5 symmetric configuration, 2 charged supertubes, and also 3 charged spectral flowed supertubes. So the details of which background we're describing is encoded in the parameters for the embedding of the null currents. And so the null currents involve the J3 directions of SL2 and SU2. And they're null, so there's some condition on the parameters. We've normalized by hand the first coefficient to be 1, since it will never be 0. And so in the supersymmetric case, the S spectral flow parameter is encoded primarily in L2, which describes the J3. So this is the parameter. You can think of this as describing the angular momentum, how that has to be realized in the coset. And the rest of the parameters are as follows. The momentum, the y momentum is quadratic in S, so S times S plus 1. And that's in L4 and L4. And similarly for the non-supersymmetric case, we have independent S and S bar inside L2 and R2. Occasionally sometimes it's convenient to parameterize them in terms of M and N, which are the angular momenta in space-time, in the two usual U1s inside S3. And in the non-supersymmetric case, the null condition, this quadratic condition, ends up giving you a slightly more complicated expression for L3 and R3. So there's a wealth of stringy physics encoded in these models that we've been exploring over several years. For instance, the two-point function of some high-energy probes encodes an additional time delay beyond the supergravity prediction. There's a rich spectrum of D-brane excitations, which are sensitive to the sub-string scale microstructure of the configuration, by which I mean the separation between individual NS5 branes. One can generalize this wall-sheet construction to non-circular supertubes. And interestingly, there are families of computable heavy, light 4-point functions, which you compute from non-trivial worldsheet 2-point functions, including an a priori surprising match to the holographic CFT. A priori surprising because these quantities are not guaranteed to be protected, but it turns out that even for the JMART backgrounds, there is some accidental protection at hand, that the supergravity and worldsheet and holographic CFT all agree on the value of this 4-point function. And so the work in progress that we're undergoing at the moment is to take a final look at the spectrum, the perturbative spectrum, especially the BPS spectrum around the supersymmetric backgrounds, and to identify in particular these ergo region modes. So in the supergravity sector, we can classify the supersymmetric excitations, and this agrees beautifully with the linearizations of superstrata that Masaki has been studying in recent years. And you may remember that we started with a 10+2 target space. So we had two time-like directions to begin with, so we have two notions of energy before we gauge one of them away. It turns out that the SL2R energy approximates the local energy in the core of the background, while the energy defined by the T direction approximates the asymptotic energy. So then there's a natural prescription that these ergo region modes can be identified as those which have positive frequency with respect to SL2R, but negative energy with respect to T, and this checks out nicely. And for instance, for these quarter BPS supergravity fluctuations, one can analyze the corresponding wave functions and ask whether these agree, whether this prescription agrees with whether this wave function is well localized inside the ergo region. And there is beautiful agreement for the supersymmetric solutions that indeed such modes are primarily supported in the ergo region. So everything is nicely consistent there. And at the moment we're in the process of analyzing stringy ergo region modes. And we do seem to find also massive string states which have negative energy in the same way, that there is some parameter space there where even though the string is massive, there is some space of states in the ergo region which are ergo region modes. And therefore it's interesting to investigate whether the JMART emission has a stringy component. One would expect yes, and to quantify how strong or weak the effect is. I think that's my last slide on the first story, so I'll pause in case there are any more questions. Yoav has one.
Does the ergo region exist if one includes string loop effects? So does GTT become non-zero?
If one includes string loop effects, everything here is explicitly excluding string loop effects, so I cannot answer directly. I mean, I'm not sure how I would. I mean, defining an ergo region, the way I know how to give a definition relies on classical geometry. I guess you would translate it into whether there are excitations with negative energy after string loop effects are included. But okay, we haven't done that calculation, so I can't say yes or no. Okay, I see no further questions. So then let me move on to the second story. This is about heavy light correlators in ADS5 CFT4. This is based on work in progress with my postdoc Sasha Chukov, who is here. And after we got started, we learned of related work by Stefano Giusto and his student Sandro Rosso, which appeared earlier this year. And there is also some parallel work by Stefano Giusto, Rodolfo Russo, who's here, Rosso, and Tsongkang Wen. So I'm interested in computing heavy light correlators in ADS5 CFT4. These correlators, of course, contain valuable dynamical information about the theory and its heavy pure states. Over the last several years, there have been many results on computing heavy light correlators in ADS3 CFT2 and in extracting information about all light correlators by taking certain limits. And this is quite powerful because using Witten diagrams is particularly difficult in this case. There's also been a lot of recent progress on computing correlators and also integrated correlators in 4D n=4 supersymmetric Yang-Mills theory. And we got excited about this topic after a nice seminar given by Heineck Paul, who I'm mentioning here, in a very incomplete list of references when he came to Southampton a little over a year ago to tell us about these developments. So there's a lot of interesting physics to explore here. And just because we're a broad audience, let me flash the canonical slide introducing this holographic dictionary between n=4 super Yang-Mills and type 2b theory on ADS5 times S5. Okay, so there's an explicit map between the parameters on the two sides of the duality. And I'll be working in the supergravity regime in ADS5 times S5. That means I'm at large n and large lambda and taking always the leading terms in 1/n and 1/lambda. I'm interested in half BPS operators, a subset of half BPS operators. So as we heard about, thanks Samir, as we heard about yesterday, the field content of the gauge theory is that we have all the fields in adjoint representation. We have a gauge field for valve fermions, and I'll be focusing on a subset of the 6 Hermitian scalars. The gauge invariant operators are composites involving traces of gauge indices. And I'm going to consider the combination Z, which is a complex combination of 2 of these scalars, phi1 plus I phi2. And particularly, I'm interested in heavy multi-traces, which are products of multiple powers of trace Z to the Ki. So these are half BPS chiral primary operators. They live in short multiplets, and they have conformal weight equal to a particular U1R charge in the SO6 R symmetry group. And as we also heard yesterday, coherent superpositions of these heavy operators with the conformal dimension of order the central charge are heavy states that are holographically dual to a family of bubbling solutions constructed by Lin, Lunin, and Maldacena. In this family, one can also think of states which are less heavy than this, but generically, these will be heavy states. The solutions involve only the metric and 5-form field strength, and they're characterized by a coloring of a 2-dimensional plane into black and white regions, denoting a boundary condition specifying which of three spheres in the geometry is shrinking smoothly on that plane. And so this is a celebrated story, and ensembles of these microstates give rise to singular ensemble geometries, and these can be the whole story here of taking extremal limits of non-extremal R-charged black holes, which have finite size horizons. When you take the supersymmetric limit of those R-charged black holes, the horizon size goes to 0, so it doesn't have a finite size horizon. One can think of it as a small black hole, or just a singular solution. And so there's an old story that perhaps by coarse graining or taking ensembles of these LLM geometries, one can have an idea of the microscopics of that singular supersymmetric limiting solution. The line element of the LLM solutions involves, as I said, these three spheres here. And we won't need all the details of this, but the physics is that the solution is determined in terms of a single function z, which satisfies a linear PDE, and imposing regularity at y equals 0 leads to a boundary condition, again, that either one of these three spheres has to shrink smoothly, and which one is shrinking smoothly is encoded in this boundary condition where the z is limiting to +1/2 or -1/2. And that gives rise to the coloring of the two-plane into black and white regions. We're going to be interested in a family of backgrounds with a single black region, so same topology as the vacuum, whose boundary involves a ripple on top of a circle, okay, an area-preserving ripple deformation, which you can describe in plane polar coordinates by the square of the radius having a simple periodic ripple. And for concreteness, I'll be focusing on little n equals 2. This particular profile has been considered before in this work that I show you here. Okay, so when alpha equals 0, this is just the circular droplet, which corresponds to the empty vacuum global ADS5 times S5, and the metric is on the slides here. The three spheres, of course, one of them becomes the three sphere of ADS5 and the other one of S5. Okay, so I will invite you to use your imagination to color in the interior of these line plots with black for the interior of the droplet and white in the exterior. So how should you think of this configuration as describing the vacuum? Well, when you're in the white region, you're far away in ADS5, you're not close to the center of it, but you're sitting at the north pole of S5 where the S3 has shrunk smoothly. As you come in towards this region, at some point you get to the center of ADS5, and you're still sitting at the north pole of S5, but as you move in the interior, this is still part of the space-time, you're moving on the S5, but sitting at the center of ADS5. Okay, so I'm interested in this middle solution, which is a ripple deformation, but it doesn't look much like a ripple until I plot, at least for your imagination, the ripples of slightly higher n. So this is n equals 8 here, where you can see it. Here, this looks a little bit more ellipsoidal or something, but it's not quite an ellipse. It's just the n equals 2 ripple. So we're going to work perturbatively in alpha, small alpha, to order alpha squared. And if we just look at first order in alpha, this solution describes a linearized supergraviton around the vacuum. And when one computes the background from the LLM description, we get powers of this quantity sigma equals r squared plus cosine squared theta, which is not a particularly convenient formulation of the solution. It's not good coordinates for exhibiting the fact that this is a single particle chiral primary. And so it's convenient to make a linearized diffeomorphism to put the order alpha fields into the standard form of fluctuations around global ADS5 times S5, as goes back, I guess, nearly 40 years now, and imposing the Donder-Lorentz gauge. And so this has been done also fairly long ago in a paper that was mentioned yesterday for different reasons. And one has then a nice form of the solution in terms of the metric and 5-form field strength of a single particle chiral primary. Okay, so these involve harmonics or scalar harmonics on ADS5 and on S5, and this is exactly the standard form of those fluctuations. So at order alpha squared, we of course have to do some work. When one computes the LLM form of the solution, one is again faced with these powers of sigma, which are inconvenient to work with. And it's much more convenient to construct the diffeomorphism that puts the second order metric into Kaluza-Klein form and into the Donder-Lorentz gauge. When one does so, the resulting second order metric is not so pretty. It's algebraically complicated, but it is nevertheless in a form which is convenient to compute holographic correlators. And then we run a standard perturbation theory of a linearized probe. For the light probe, we take the dilaton or Ramon-Ramon axion, whose fluctuations satisfy the 10-dimensional minimally coupled massless scalar wave equation, just box phi equals 0, on this non-trivial curved background. And we expand everything as one usually does in perturbative alpha expansion. So the first order, we're just solving the wave equation on global ADS5 times S5. The next, that's the 0th order if you like. At first order in alpha, I have a source from the first term, and a second order in alpha, I have two sources. The boundary condition is the standard one for computing holographic correlators. I require that the fluctuation field has the form of a delta function source at a particular point on the boundary, which is specified, that's input to the calculation at order alpha to the 0. And then I read off the response at order alpha squared, and that response encodes the correlator of interest. And because we're working in perturbation theory around global ADS5 times S5, we expand everything in spherical harmonics on the S5. Okay, so appropriate scalar vector tensor harmonics. And then again, expand the coefficients perturbatively in alpha. So at order alpha 0, we have to specify this physical input corresponding to the particular correlator one is interested in. And there are two such sources we've been investigating so far. One is to take just the trivial harmonic on S5, which corresponds to the 0 mode of the dilaton or axion on S5, which corresponds to a dimension 4 descendant of a single particle dimension 2 chiral primary, the same one we have in the background, which is O2 equals trace Z squared. And one can also think about higher harmonics. It's a bit more convenient to stick with the 0 mode, 0 angular momentum but one can take the harmonic, for instance, Y20, which corresponds to a particular dimension 6 descendant of a dimension 4 single particle chiral primary. And since the first order background involves the harmonics 2 plus minus 2, there's some straightforward harmonic decomposition of these perturbative equations. I have the trivial harmonic at order alpha to the 0. One solves exactly the first order problem and gets harmonics 2, 2, and 2 minus 2. And then at the last step, one projects on the harmonic of interest, so we project back on the trivial harmonic. And the first line is just taken, the solution there is taken by choosing the appropriate bulk to boundary correlator for with the operator dimension appropriate to the correlator of interest. And so then you've set everything up, you can just crank the handle, compute the sources on the right-hand side of the equation. It's easy to say, but it's not so easy to do. It requires work. But then, did I lose the microphone? Once you've done that, you can rewrite the sources in terms of bulk to boundary propagators. So these sources for the order alpha squared equation involve, after rewriting, products of 3 bulk to boundary propagators. When you then solve the equation, you invert it, you get an integral over a product of those 3 bulk to boundary propagators and a bulk to bulk propagator. And when you read off the response at the boundary, you end up with an integral of a product of 4 bulk to boundary propagators. And so the result is naturally expressed in terms of the D functions that naturally appear in holographic correlators. And so just to give a little bit of meat to those words, when one rewrites global ADS 5 times S5 in Poincare coordinates, one can write down the explicit expressions for the bulk to boundary propagators and the D functions. It's convenient to fix, as usual, 3 points of the correlator to be 0, infinity, and some particular point 1, which is the north pole of the S3 at the boundary. And when one does so, the D functions that appear in the gravity answer become related functions known as D hat functions. And so from the supergravity solution, one can also read the energy above the vacuum and the angular momentum. So when alpha is order 1, this is a heavy state, but when alpha, meaning order 1 with n, I'm taking alpha small. So if I take alpha small but not scaling with n, this is sometimes called a perturbatively heavy state. So the dimension scales like n squared, but with some small coefficient. And it's interesting that the CFT heavy state is not known in precise detail as things stand. It's expected to involve a coherent superposition of multiple powers of trace z squared together with powers of other single traces as well, and this has not yet been fully worked out. But there have been some partial proposals in the literature of specific types of coherent states which approximate what you want, in the sense that some basic observables agree with the geometry, but there's some precision holography needed here to pin down the precise form of the heavy state. However, what we do know precisely is the small alpha limit. So I showed you the order alpha fields. They're precisely the fields of a particular chiral primary, which is trace z squared. So the perturbative expansion of the heavy state in alpha is known explicitly. And we can use this fact to study the all light limit of the heavy light correlators computed from supergravity. And based on results from ADS3, one expects that the gravity calculation contains information about the S channel of the light correlator, which I denote here. And so I have these 2 chiral primaries which came from the heavy state, but now they've become light fields, CPOs in this correlator. And this is the dimension 4 descendant that was the light probe also in the gravity calculation. And so I have a correlator here, which is all light, where one is again sending the 3 points to 0, infinity, and 1. And one can extract a stripped correlator G24. It's convenient to analyze the resulting correlator in Mellin space. And in the Mellin transform correlator, just two slides, the poles encode the twist of the single trace operators exchanged in a given channel. And the Mellin transform is given just here. Okay, so this is the last main slide. We see some very encouraging preliminary results in what we get from gravity. That we have a particular pole at s equals 2 with some particular polynomial in T, plus some polynomial terms which are still undergoing checks. So not everything is completely as we would like at the moment, but this main physical part seems to be coming out very nicely. And this above pole, the term with the pole here passes a nice cross-check that the amplitude is related by a superconformal Ward identity to a previously known correlation function of 4 chiral primaries. And I would like to say here that there's been a parallel calculation that I expect Rodolfo will talk about after lunch by Stefano Rodolfo and collaborators with a different methodology that has a limit that agrees with this pole here. And I'd like to acknowledge some help they gave us with a crucial reference to assist with us with this check of the superconformal Ward identity. So there's a nice parallel story here, which you'll hear more about after lunch. Okay, so I'm done. I'll leave the summary there, and stop here. Thanks.
Questions?
I have a technical question. Is the ripple you're using, does it belong to the consistent truncation that gives you gauge supergravity in 5 dimensions?
No, for that you'll have to wait till Rodolfo's
What is that?
talk,
Okay, which value of n for the ripple is in the consistent truncation? N is 2 or n is 1?
So n equals 2 is what I'm focusing on here, and the solution that Nick is talking about is something everybody will hear about after lunch. It's also for n equals 2. So at order alpha, these solutions are the same.
Right.
The difference comes at order alpha squared and higher. So there, of course, when one has a perturbative solution at order alpha, there are infinitely many completions. So that there are infinitely many LLM profiles, if you like, that start off with the same linearized deformation. I'm taking a particular one here, but there are other ones that you'll hear about later.
Other questions?
It's a technical question. So you are computing the bulk to boundary correlators in Poincare ADS, and then you are moving to global because
I'm in global ADS, but it's convenient to use Poincare coordinates for global ADS.
I see. And then you are computing, but you are computing the bulk to boundary propagator in your solution, or I mean, I didn't understand.
Global ADS. So the propagators are for global ADS 5 times S5 because I'm in perturbation
But
theory.
when you go from Poincare to global, you have a problem because in global you have many patches of Poincare. So if you just take a vanilla Poincare, it has actually multiple images. So it's not a good bulk to boundary.
It's still a global
the mic.
ADS.
Here.
It's just a coordinate choice.
It's a Euclidean, so then there is just a change of course.
Oh, okay.
Euclidean
Okay, you don't have the
Yeah.
global ADS with
Okay.
multiple Poincare patches. Okay. That's what it. Okay, thanks.
Okay, actually, I also had a technical question, maybe to both of you, about the first part.
Mhm.
So you have this SL2 times something, quotient, etc. Now, in the old cigar geometry, when you had SL2 module 1, there were sort of 2 ways of understanding it. One is how Witten did it. It's literally what he really meant SL2R, quotient 2-1. But then when people study path integrals, you have the Euclidean SL2C, quotient SU2, quotient 2-1. Which is the one you're doing here?
The first of the two.
The first one. So, but now the U1 is not time-like, but it's
Yeah, so
Like
here
thing.
there are, if you like, a pair of U1s, but really the space we're quotienting is a cylinder. So these are just null U1s on a cylinder.
I see. So it's really the time-like SL2R model, and you take a null quotient of them. Okay. If there are no other questions, let's break for lunch. When are we meeting next?
2 o'clock.
We meet at 2 p.m. Let's thank the
I want to
speaker
make
again.